Paul obtained his undergraduate and PhD in chemistry at the University of Antwerp in Flanders, Belgium. After compulsory military service, Paul went for a postdoc to McMaster University in Canada with Professor Richard Bader. I didn't know that in Western countries there is a compulsory military service. I thought that was only in communist countries. Paul was then
Is that a question, Christoph?
European, but it was possible to avoid. I avoided it even under communism, this compulsory military service. So Paul was then European Union funded Marie Curie fellow at the University of Cambridge, Great Britain. He was appointed as a lecturer at UMIST, which is a precursor of the Merge University of Manchester. And if you go to Manchester, you will see beautiful statue of Archimedes and jumping out of water. And that used to be a kind of a symbol of university at the time when I was young. Paul currently is the professor of chemical theory and computations at the University of Manchester. Paul's activity, past and present, is focused on the areas of chemical bonding, bioisosterism, molecular similarity, QSAR, QSPR, valence shell electron pair repulsion, machine learning, and he was one of the precursors in this field because he started it more or less in 2007. Algorithms for quantum chemical topology, visualization, molecular dynamic simulations, intermolecular interactions, PKA prediction, F-flux force field, ionic liquids, crystallography, polymorphism, computations of chemical insight with relative energy gradient. Probably it would be faster to count, to name what you were not doing than what you were doing. His main research activity is design of machine learning potentials, F-flux, and the in-house interpretational method called relative energy gradient, and he will be talking about this today. He chaired a Faraday discussion meeting on chemical concepts from quantum mechanics, chaired a UK QSAR meeting, currently got 7 PhDs and 5 postdocs in the research group. A lot to be done with such big bunch of people. Recipient of the Richard Bader International Prize. He has published already close to 300 publications and 4 books including 35 single author publications. Paul has been awarded an FCRC Established Career Fellowship and also ERC Advanced Grant. That big congratulations, Paul. I don't know how you have done this, but it's to get ERC grant, that's really quite something. So Paul today will be talking about the relative energy gradient method. Paul, the screen is yours.
Thank you very much, Christoph. If that was a question, I tried a lot to get the ERC grant. It didn't come right away, so one has to be tenacious, I guess. But thank you very much for this long introduction and your kind words. And for this platform here to speak about it, this REG method, where I will not speak on crystals, but I understand that this is allowed. You call it complementary fields. And I think this method is so general that it can be used in crystal. In fact, there is one study that I briefly mentioned at the very end to show that it can be used there, because a more colloquial way of saying what it does is to prove that a fragment behaves like the total system through an energy profile. But all that will become hopefully clear. As you know, I have this theme here. It is a common theme to everything that we do. Does this cursor work here? Can I mark with this? Can people see this move? So
yes, we see it.
Okay, thank you. I don't have a laser pointer, so I'll use that if that's okay. So I think quite a few people are familiar with well, cutane, quantum chemical topology. So I'm not going to explain it or even give a crash course in it. I'm just going to focus on a few features. So we have a simple molecule here that falls apart unnaturally, as I always say, in terms of its topological atoms. And you can do a 3D view of that. Visualization has moved on a lot since 94. Back then, we were the first to present 3D pictures of atoms in molecules. The reason I call it 2.5D is because real 3D is, I guess, 3D print, where we indulged a little bit in that technology and made, if you like, a hardware equivalent of topological atoms. So no review, just reminding ourselves that there are no gaps between the atoms. They have sharp boundaries. They don't overlap, and you can then call that space filling. And then a number of other features which I don't have time to discuss, but I'm hinting here at alternative ways of defining an atom or charges, atomic charges. Hirschfeld, for example, the original Hirschfeld needs a reference state, but we don't have that in cutane. And this is useful, or actually pivotal, I think, in force field design, or as Christoph said, the machine learned potentials. There's a single formula that is a 3D integration, a volume integration of some density. This can be the electron density itself, giving you then the number of electrons inside the atomic volume. So that all the properties come from one formula, and that helps, I think, in building robust foundations for a force field where you can say that all the energies and the charges, multipoles, etc., are all coming from the same partitioning, which is not the case in certain alternatives that I cannot explain for time reasons. REG, which I will explain in a few minutes, in this case operates on atomic energies provided by the IQA method that I think is probably, you may have heard of it, very much a cutane-like method, where we are starting here from a general energy expression. You may recognize the kinetic energy here, and then here, very easy non-quantum part, just the nuclear repulsion, then the nuclear electron attraction, and then this beast, if I may call it like that, is very complicated, not at Hartree-Fock level, but if you have correlated wave functions, CCSD, then this gets very big, but then it has everything in it, the full behavior of electrons interacting with each other. It has this fine structure, which allows you then to associate certain physics and chemistry with the various terms. This here is important if you want to measure, if you like, or calculate the degree of covalency of a interaction. By the way, this is giving you a scale of numbers. It's a spectrum. So the term non-covalent is a bit drastic. It's actually a sliding scale. And the last part I'm going to omit today. We don't need it for the case studies I will discuss. This is very, very big in size and time consuming to calculate, but then it gives you access to dispersion. So like I said, with the physics comes the chemistry, and there are various keywords that can be associated with each of these terms. But there is also the kinetic energy that is going to come in, and we're going to work with that in the first case study of hydrogen bonding. And I can add to this kinetic energy naturally two other potential energy terms that are intraatomic, so the electron-nuclear attraction and the electron-electron repulsion. And we were the first to interpret the IQA numbers that came out and made a link with a more traditional potentials, one part of the Lennard-Jones potential and the Buckingham potential. I'm happy to amplify what these publications were telling us. But here, for example, the first study was fitting these numbers to Buckingham potentials and so the exponential behavior that you see there. And the fits were very good. We also recovered combination rules. We also showed that Buckingham was a better fit than Lennard-Jones, which I think the literature would say. And then later on, we actually saw that there was also transferability, so that the actual fitted parameters had chemical meaning. The electrostatic energy is the second type, very important. It's calculated through a 6-dimensional integration. So here we have a quantum atom, a topological atom, and another one. And you literally are calculating, well, maybe I should show the formula. In this 6-dimensional integration, you're calculating every bit of charge here interacting with every other bit there through this well-known Coulomb shape. And in the exchange energy, you're actually doing the same. You work with a 6-dimensional integration, but here you have a different integrand referring to the second term of the previous slide, if you remember. This is a quick dip into the behavior of exchange energy in the water dimer. It's depicted a few times, but here is one. So this is the global minimum, water, and here is a hydrogen bond. Now, what am I plotting here? Forgive me for the kilocal per mole, that's my collaborator. I prefer kilojoules per mole, but so you have minus this quantity here because it's negative and it has to be positive on this logarithmic scale. The internuclear distance is here. It's logarithmic, but it doesn't have to be really. So the biggest contributions you find here, these are the actual OH bonds themselves inside the water. And then the HH interactions are well, a couple of order magnitudes smaller. And then again, 1, 3, 1, 4, weaker and weaker. But then anomalously, the OO exchange is actually quite large. You can imagine there's some kind of band here that expresses literally that an interaction gets weaker as the nuclei are further apart. But here, this is an interaction that is not in that band and shows that, same for hydrogen bond, OH, that there is a bit of bonding going on there, that there is a strong interaction with some covalent nature. Right, so relative energy gradient, what is this? Well, without maybe realizing it, the average chemist, I mean, the synthetic chemist, the sort of back of the envelope chemist, is thinking in terms of a few atoms governing the behavior of a system. For example, the hydrogen bond itself. So I am going to work here on work with the water dimer. Is it safe to say that these two monomers are held together by a hydrogen bond? Well, quantum mechanically, of course, is much more going on. There is 6 atoms all interacting with each other and with themselves. Within each atom, there are all these energy types that you have to consider. What gives me the right to say, well, the O4H3 interaction really is calling the shots here? And the REG method is going to compute an answer, in fact, a ranking, where you can then interpret the highest ranking as the one that is in charge. Okay, so it's inspecting the relation of each energetically partitioned term to the total energy in a way that I will make clear. Out comes then a twofold partitioning, not only in terms of where it is, so the number of atoms or groups, functional groups, but also the energy types. And I'm going to work with only 3 here. The example I show is a Hartree-Fock calculation, which is sufficient for us. It doesn't have any correlation, so that's all. Now, we didn't come to this REG idea right away. Sorry, that's the slide after this. But so just to set the scene further, there's going to be 36 terms here, 15 electrostatic, 15 exchange, and then 6 intraatomic terms. And another important ingredient is that I cannot study the hydrogen bond by just looking at one fixed geometry. What I need is a sequence of geometries. So I need something dynamic, and I need a coordinate to control this dynamic change, which is going to be simply the distance here between the 2 atoms here, so H3 and O4. This can be, in the case of a rotation barrier, if you want to explain the nature of that rotation barrier, it just will be the dihedral angle controlling the sequence of snapshots that you then analyze. So the question is then, which of these, in this case, 36 terms or sums thereof has a profile, an energy profile that resembles the profile of the total system? Because it's a comparison. It's always individual versus total, hence the word relative. Well, you start hitting a combinatorial explosion soon. If you have, for example, a subset of 3, so you would just pick, for example, this atom and that atom and that atom, then all 3 are one possible explanation, that is the energy behavior of whichever way, in electrostatic, of these 3 would then be, well, it would actually be a crazy proposal, but mathematically you'd have to consider that. But that's not the way we're going to work, because that will be quite horrible to consider that. There is another point to keep in mind. So here we have the total energy profile. Imagine that we have 2 candidates, B and A, and we're just going to measure the similarity, if you like, between A and the total and B and the total by a simple RMSE. Then you see that A has a lower or high similarity, is a lower value of RMSE than B. And that's just because it follows the total here exactly, whereas B doesn't. But really, the human eye would say that this B is actually following the shape of this much better. So working with RMSEs is not the right thing to do. So what do we have to do then? Well, another thing that we have to consider is that we look at one segment at a time, and I'll illustrate that by means of Lennard-Jones. This is a well-known shape of that potential, consisting of propulsion and dispersion. And here we have it. The green part is the total Lennard-Jones, and then we have a stationary point there, which is going to define two regimes, the left segment and the right segment. And we ask ourselves, is there like a narrative? Can we say that one of these terms is explaining the behavior here or there? And that's indeed the case. It's natural to say, well, the total curve is really dominated by this repulsive potential. So that's going to be the narrative, which is a bit simple here. But you get what I'm, hopefully you understand what I'm getting at here. Same for dispersion, that as the two argon atoms come from infinity to the equilibrium point, for example, that's going to be dispersion that is responsible for that, where this repulsion is not really doing very much. It's this red curve that is really pulling. And so we can say that each energy segment is explained by its own type of energy. And we keep that in mind because that's going to resurface in the analysis of the water dimer and later on by female. Okay, so time to maybe a little bit take stock and where do we go from here? So we have the total energy as a function of this control coordinate, the hydrogen bond distance, for example. And then we have one of these 36 energy contributions that has its own profile, G. Now, we're actually not interested in F and G by itself. We're interested in the relative behavior. How is one behaving relative to the other, which is going to be done by a ratio. And here, to fix our thoughts, so here we have the system again. We have the total energy profile, which looks a bit shallow. That's just because of the scale. And this is kilojoule per mole. It's because I want to put the golden or orange plot also on this figure. And it is typical that atomic interaction energies are always larger than total energies. So that's why scale here forces that to look more shallow than it usually does. We have, I think, 10 snapshots, geometries from A to J. And we're going to look at the correlation between them. So why not call this a correlation curve? So again, the total energy is here. And this energy that I'm following here is plotted on this y-axis. And then I have two regimes, if you like. So from J to D, so that's from there to there. That's going to be eventually called the right segment. So there's a stationary point there. And then the second regime is ABCD, if you like, belongs to it. That is the compression part. Okay. And the good news is that there is largely a linear behavior for either segment. This fit here is very good. This fit is not so good, but it's still decent enough by its Pearson correlation coefficient it will pass. The single fit here for the whole profile is not a good idea. That sort of reinforces that idea again of each segment has its own narrative. And yes. So moving on, we then can of course write down this. Ultimately, the total energy is the sum of the individual energies. There is a small error on this because I didn't say that, but some people may be aware of this. that the atomic integrations come with some noise, if you like. It's a numerical quadrature. So the error can be around a kilojoule per mole, but that is acceptable compared to the actual signal, if you like. If you study a barrier of, say, 12 kilojoules per mole, that's acceptable. This expresses that linear behavior that we have. So here we have the REG coefficients. And it's those that are going to be ranked. So we'll find out which is the steepest, either way, positive or negative. It's a bit of mathematics. It's just the normal least square fit. With one detail is that we have to shift or translate the profiles by their own mean, just to make things all work out. I mentioned the Pearson coefficient. That's of course well known. So we typically find 0.95, 96, so pretty good fits. If you find a poor fit, it means that the REG is breaking down. It means you shouldn't use it. You should then define more segments. In terms of semi-quantitative analysis, either REG value is positive. That means that, I don't have a picture for this, but you can imagine, is that the individual contribution is reinforcing, it has the same sign as the gradient of the total profile. So they are in sync. So I don't know whether you can see that, in sync like that or like that. Negative if it's plus minus or minus plus. That's negative. That means that the energy contribution is working against the behavior of the total energy segment. And like I said, you can then rank. So if this is a bit abstract, let's see that working out now. So here we have, again, our total energy profile, kilojoules per mole, typical distances. And then we can produce tables like this. We're first analyzing the compression regime here, where this one is the highest REG value. So it means that a steric effect, that the energy increase of this as this atom gets squashed upon approaching the other one is the main cause for this energy barrier. This one is next, almost same in strength. Does that intuitively make sense? Well, this means here the classical electrostatic energy was that first term, if you remember, rho R1, rho R2. That's just the massive repulsion you have between the two oxygens is very much contributing to this barrier, as are the positive charges of the hydrogens. Okay, so this is quite intuitive. For the other segment, the right segment, we see right away that there is electrostatic, the contributions are all electrostatic, which I like to think is in line with a model you may have heard of that was popular, formulated in the 80s, looking at a great number of van der Waals complexes and explaining them electrostatically. And here, zooming in on that hydrogen bond, we see that there is also forget the C, there's exchange going on there as well. So there is a certain covalency in that hydrogen bond, although predominantly it is electrostatics. So in summary then, so the left fragment here is kind of dominated by this contribution of the steric effect of O4, which is completely in sync with that, and this one for the other segment. Right, so that was where it started, if you like. Then I'm going to discuss the case of biphenyl, and I realize I'm actually and probably going over my 35 minutes. Please stop me if I'm talking too much. Biphenol is an attractive study because, first of all, well, looking at crystals, it's very frequent, also in the PDB, but in the Cambridge Structural Database as well, in drug design. But in particular, there is this controversy that you may have heard of, like why doesn't it like to sit flat? I mean, the equilibrium geometry is has this dihedral angle of 44 degrees. I'm not going to dwell on how that's actually calculated. There's a whole study on just that. You need a pretty fat basis set to get those numbers, but we have used that here. And we're going to use as a control coordinate tau, which is the dihedral angle of these four carbons there. And the barrier that everybody focuses on is the one going from a flat biphenol to one that's almost 45 degrees. But there is another one. It doesn't like to sit perpendicular either. So we can also study that, and we'll say something about that. This is a little technical thing. That's the integration error I mentioned before. It seems to be very well under control here. The error is just less than a kilojoule, half a kilojoule, I think, per mole. So we can live with that because the actual barrier is of the order of 13 kilojoules per mole or 4. So a few percent. And we're going to take 10 number of steps, 10 degrees each. Now, there's two slides setting the scene because it was very controversial in the early 2000s. Part of that, I think, is the doing of QTEM itself. So where you see a bond critical point here between the two hydrogens, and one of the first ones, a Polish scientist, Cisłowski, who was then in America, interpreted that as a repulsive HH interaction, which we will see is not correct. But that's, of course, mysterious. Why would there suddenly be this? Why would there be a bond critical point associated with a repulsion? Now, it should be a signature of a bond, of something attractive. Then there was a big pause, and then later Bader and co-workers started criticizing that. They also had looked at lots of polyaromatics, seen lots of BCPs in there, and for reasons I cannot expand here, we're confident that these BCPs were always expressing stability. Then the non-QTEM contributors here to the story were saying that there is no HH bonding there in this planar biphenol, and echoed the textbook answer. So the bottom line is that the problem of this BCP stayed. Bader immediately rebut this. And then there was a counter rebuttal, so quite amusing. They were fighting the literature. And then, Mata, again, saying, well, no, this is really stable. And others as well having their own arguments. And this is a very interesting study that I don't have time to expand, but it's really worth reading. And they were, with admittedly partial data, adamant that as the two hydrogens came together, they were really happy doing so. There was quite a bit of increased exchange between them, which is a signature of a covalent bond. So yes, then Van Alsenoy, they confirmed again a net attraction between the two ortho hydrogens, H2, as we will see. And so we are left with a story that is unresolved, where there is stabilizing and destabilizing interactions. And the question that REG is then going to answer is, we should look at all possible interactions and literally, if I can use that word, compute the chemical insight, not impose anything, but just really say, let's calculate what comes out at this level of theory with just Hartree Fock. We have 22 atoms, but we just need to focus on these 7 by symmetry. And so we have quite a few terms there. So we're first going to analyze with individual energy. So not only atomic, but also by type. And we're going to look at the rankings. The table comes up in a minute. But we can just intuitively have a quick look and find out. So this is the total energy here in blue at the left-hand side, red at the right-hand side. And we see that this one here is actually really calling the shots, which is like a steric effect between these two here. So that's going to be a textbook confirmation. Here, for the less discussed perpendicular barrier, we have the exchange between these two. That's going to be basically a story of loss of conjugative effects throughout the phenol. I see I'm running out of time, but there's a very nice metaphor in this paper with a football, how to analyze a goal of a football team. But yeah, maybe in the questions I can see how REG and football commentators are similar in a way. So here's the table then. So here's the planar barrier. I'm going to skip this here for time reasons. But what comes out as the top is this steric effect. So that clash, which is a textbook answer, is confirmed. That comes out of REG. We could also see that the volume of these are shrinking to its pronality. So it's, they breathe, these atoms. They're like bubbles. At 90 degrees, they're maximum in volume, and they shrink. They get squashed, and they don't like that. And that's a steric effect. That the intra-atomic energy, possibly kinetic energy, is really not happy with that. Let me skip that one. At the other end, for the planar barrier, we have the contribution that works most against the planar barrier. So that's going to be a stabilizing effect. And we can also relate that to the volume. So here we have the tau is marked here 10 degrees, 10, 20, 30, and so on to a perpendicular. And you see that as the volume is increasing of this atom, that the energy is going down. So you can depict that intuitively. What about this one then? The exchange energy? Well, it's also opposing the barrier. So it's not helping making that barrier. So yes, it is an effect that is, it's an attractive interaction, which is exactly what you find when you form a covalent bond. So that is true. And you can say the BCP is expressing that. Now, Angel Pendas has studied the formation of homonuclear diatomics, and he's seen that as well, that you have the two free atoms coming together and each being sterically very uncomfortable about that, but they're over that uncomfortable, that destabilization is overruled by a massive exchange effect. Okay, then you can say, well, what about this type of IQA energy where you are summing the various contributions? So to the interatomic contribution, you are summing the other interaction energies, all the other B atoms that interact with A. And then you get a much simpler table. So I'll just focus on this one, the planar barrier, where this time you see that the ortho hydrogen, which was at an atom at a sort of at the previous level, which is more fine. This is a coarser level of analysis. That was calling the shots. That's now lost because there are two things happening at the same time here. There's this steric clash, but there's also that bond formation. So that means then that in the bigger picture, the red one here is H2. That's not so steep anymore. Instead, it's going to be C2 that is calling the shots, and that's that atom. And that reminds me of the saying that if two dogs fight for a bone, that the third one runs with it. So this atom can then be seen, which is new type of intuition. I don't think chemistry books would say that these are responsible for the barrier. Yeah, so the ortho one and the story then for the perpendicular barrier is actually all about these. Okay, Christoph, 37 minutes. Do I have another 5 minutes or?
Yeah, carry on.
Yeah, sorry. I squeezed too much in it. It's literally 3 quick slides on another application, and I give you the conclusion. I think I have 28 slides. So we work on biological systems. You could say, well, this is all very simple. Does it work for enzymes? Well, yes. This is an hydrolysis. So this peptide bond here is going to be broken by a water that first attaches nucleophilically and then leaves the peptide in the original severed here. There's nothing controversial about this enzyme. It's it arises in HIV context. Here it is. We don't do all the atoms. We just do 133 atoms. Here they are. There we have our water again. This is the peptide bond that's going to be cleaved. Now that leads to not 36 or 484, but a good 17,000 possible interactions. So again, I think the word compute chemical insight, the compute is accurate, done by a program that is available, reg.py. And yeah, sorry, I don't have time to discuss all the details, but so here we have just a single segment to study by the typical 10-ish steps. And that's the last slide here. So the sort of results you get from that is a whole bunch of, well, we looked at Vx by its only here because we wanted to get an overall picture of bond strengthening and weakening. So if you are against the barrier, then of course you have a negative and you are strengthening or forming bonds. And you can then see here that the green arrows are all about new bonds being formed, whereas the red arrows about bonds being broken. So if I had more time, I could convince you that this is a nice arrow pushing scheme that just emerges from this rather massive analysis of IQA energy terms. So yeah, and then these sort of interactions here are sometimes the literature called through space interactions. It's always a bit of a mysterious name. It's as if the researcher knows there's something going on, but they don't know what it is. Here it comes out as an increased or anomalously high covalent exchange type of interaction. So that tells you something's going. It's almost like a glue, for what it's worth. Okay, I didn't have time to discuss this, but you can study various polymorphs through this REG analysis and look at the barrier and the origin thereof. Okay, last slide. Apologies. So here we have a number of features of the atoms that we use, the type of energies. We didn't use correlation energy. I've said many times that I think we can safely say we are computing chemical insight. We have one narrative for each energy segment. You need a sequence always. You can't do this on one snapshot. And yes, we confirm that you can safely say hydrogen bond holds the water diamond together. And on biphenyl, we have indeed this steric destabilization, but it's counteracted by this weak covalent bond. So it sort of resolves that contradiction or apparent contradiction. This is new intuition, the authors coming in, and yeah, the other barriers explained like that. And I showed you an example of an arrow pushing scheme with some through space interactions characterized. And thank you very much for these wonderful people who have left meanwhile and money from these organizations. Thank you.
Thank you, Paul, for this excellent lecture. It's time for questions and for comments. Usually it takes a moment until the first questions appear.
Let me ask my question before other people write theirs. Thank you, Paul. It's a very beautiful approach and giving chemists what they actually want to get from the calculations, right? Well, to be able to use it, I have a question: how long it takes? I mean, how big computing power you need to get this kind of information, and how much time it takes, and what's the level of theory or methodology you need to use to get a proper answer.
No, I understand. So it used to be quite horrible, but it's not anymore. So we're talking about days now. I mean, but it's like, how long is a piece of string? It's known that the IQA energies, which you can get from a program called AMOL, are much more computationally intensive than more traditional EDAs, energy decomposition analysis. So there is always that cost of getting the IQA energies themselves. But the REG itself is very fast. So I didn't show that paper, but we've invested time in making the number of snapshots needed fewer, because for enzymes you work with 150 atoms, 200, and every IQA calculation is really But so it used to be weeks back then, but now it's a matter of like an afternoon for a system. It depends on your calculation of power. It's not a few minutes, that's for sure. So does that help?
Yes, it sounds very promising.
Yeah, you were discussing this, say, not planar system. I remember we used to study benzidine dichloride, and we were observing the similar interactions, and used to discuss how they could be interpreted. And it's with this kind of systems is interesting crystallographic story, because people used to, especially old generation of crystallographers who were using point detectors, then they were searching very fastly reciprocal lattice, and were getting unit cell parameters based on the strongest reflections. And in the case of such systems, there is like superstructure. So when they were using only the strongest reflection, they were getting flat molecules in the crystal structure, whereas when the whole crystal lattice was collected with weak reflections, the final structures appeared with this bent to benzene rings. So the story was with this benzene dichloride, and probably the old data sets collected, say, long time ago, many of them are simply supplying wrong structures. But that's how data were collected long time ago.
Mm-hmm.
I have another one. How sensitive this method is to the quality of the geometry? Is it possible to take experimental geometry, like snapshots from various steps of an enzymatic reaction? Well, that's probably too far to dream for proteins, but
I think so. I think experimental geometries are good enough, because I mean, think about it. The dynamics that I showed are really over large distances. So in the case of the water dimer, you're talking about several angstroms, and with the dihedral, it's an angle, of course, that will depend on the exact positions of the four nuclear positions that feed into the angle. But if there would be sort of an uncertainty of, say, a tenth of an angstrom, which is maybe quite generous, on each of these, then the angle could vary by a few degrees. But you see, it doesn't actually matter so much.
Yeah, because it's relative, right?
The phenomenon you study is a broad thing that happens in an interval that has quite extreme boundaries, like a full rotation of over 45 degrees dihedrally, or a displacement of 2 angstroms. So I think that phenomenon will survive noise or uncertainty on that experimental geometries may have, I think. So I think it's safe. That would be my initial instinct. The reg narrative will not change, I think.
We have a volunteer who want to ask a question. Let us enable the mic. Guillermo Monaco.
Okay, can you hear me?
Yes, we can.
Oh, thank you very much, Paul, Guillermo, and thank you. I really liked very much your lecture. I have a silly question. In the analysis, which is completely self-contained about two-body interactions, can you think you can have any insight on anything which is delocalized and which is it brings about interactions of 3 or more atoms?
Yes, that's actually the case in the biphenyl case study, particularly for the perpendicular barrier, where there is like a huge conjugative effect throughout the molecule, if you like. So yes, mathematically we write everything as two-body, and well, that you may, it goes back to McGreeny's interpretation, but the full effects present in the molecule are captured by these atoms. So the answer to your question is yes, we will see beyond sort of a naive interpretation of two-body interaction. If that makes sense.
Okay. Thank you.
Are there any more questions or comments? As I do not see more, so thank you, Paul, for this very clear presentation, very interesting. Thank you very much.